Determining the pH of a weak acid solution is an equilibrium problem. Like many equilibrium problems, it can be solved using an equilibrium table, sometimes called an ice table. To construct such a table, write the chemical equation. In this case, the weak acid, HA, ionizes to produce hydrogen ion, H+, and the corresponding anion, A-, and make a column under each species. Divide the table into 3 rows. The initial molar concentrations go in the top row, labeled I for initial. The changes in molar concentration go in the middle row, labeled C for change. And the final, or equilibrium molar concentrations, go in the bottom row, labeled E for equilibrium. In this example, we are asked to determine the pH of a 0.1 molar solution of weak acid whose ionization constant Ka is 2.5 times 10 to the minus 4. Enter the initial molar concentration of the weak acid, 0.10, in the first row under the weak acid in the equation. Before the acid ionizes, the concentrations of H+ and A- are 0. Note that the initial concentration of hydrogen ion is not really 0, but its concentration due to the autoionization of water is so small compared to the amount that will be produced by ionization of the weak acid that we can neglect it and use 0 for the initial concentration. Using the stoichiometry of the balanced equation, we can enter the change in molar concentration for each species as follows. The weak acid concentration will decrease by some unknown amount which we designate x. The concentrations of H+ and A- will both increase by the same amount. Next, we add the entries in the first 2 rows to get the equilibrium concentration of each species. 0.10 minus x for the weak acid, x for the hydrogen ion, and x for the corresponding anion. We set the equilibrium expression for the equation equal to the Ka and enter the equilibrium concentrations from the table. To simplify the solution, we compare the magnitude of Ka to the initial concentration of the weak acid. If the magnitude of Ka were greater than 5% of the initial acid concentration, we would have to use the quadratic equation to solve for x. In this case, the magnitude of Ka is less than 5% of the initial concentration of the weak acid. This enables us to neglect x in the denominator. Solving for x gives 5.0 times 10 to the minus 3. This is the molar concentration of both hydrogen ion and the corresponding anion. Taking the negative log of hydrogen ion concentration gives a pH of 2.30. An equilibrium table and the appropriate equilibrium expression can be used to solve a variety of problems, including the determination of pH for a weak acid or weak base solution.